Okay, class, let's get started. Welcome back from spring break. I hope everyone was looking forward to getting back to physics class. I know I was. I love spring break, but this is my favorite class. So, welcome back. As I've said over the course of the semester, I kind of think of this class as divided into roughly two sections. I hate to do that to the universe. It's just one universe, but the way we're going to study it, we're going to kind of spend some time talking about the moving big macro parts of the universe. That was up till spring break. And now that we're back from spring break, I kind of want to switch things over to a different subset of the universe, I think. I just a minute ago changed, all semester I've had this slide, I've called it invisible stuff. That's the subset of the universe I've been saying we're going to get to. And it occurred to me just about a minute ago that invisible is a bad word to use because primarily what we're going to be talking about is light, and light is pretty visible. In fact, visible means you can see it, and the only way your eyes work is through light. That's how your eyes actually work. So you've got these little optic sensors in your head, and those things are sensitive to only light. And so when I say invisible, I shouldn't say that. So maybe I mean intangible. Okay, so there's a little correction. But so that's what we're going to start talking about today, this thing called light. And as usual, we'll start with a little bit of history because I think it's significant and worthwhile to note that probably since there have been humans, light has been something that we've been interested in and maybe would like to know what it is. But it's also one of the more mysterious and difficult to pin down. So I think, we humans are very curious creatures, and so I think since there have been humans, we probably picked up a rock and said, I want to know what that is. I wonder what that is. Well, a rock is relatively easy to study. You can pick it up, you can hold it, you can sniff it, you can lick it, you can, whatever else you do to rocks, smash it, weigh it, throw it in some water, see what happens. So doing experiments on these the macro part of the world, I think was easier. I think we've always wanted to know what light is, but it's a lot easier, it's a lot more difficult to study. Now, Newton was famous for being curious about the natural world. He called himself a natural philosopher, and he figured things out like gravity. And again, well, gravity is also tough to understand because you can't touch gravity, but at least you can watch things fall down. So Newton was also very curious about light and about color, and famously, he would jam stuff in his eyes just to see the effect of visual perception and color. And you can, please don't do this, but you can make really weird rainbows and patterns and shapes and black spots if you jam things in your eyes. Or he would go stare at the sun for a while till things started to go black on him. And he just was a very curious guy, curious maybe to the point of being not safe. So don't do any of those things. Don't go stare at the sun. We now know that that's bad. Okay. But so it's a difficult thing to study. And in fact, one of the things we're going to talk about one of the things we're going to talk about this semester is that light, in fact, it's one of those things. It's one of the standard model, meaning in the great history of physics, I think I've said this, I think I may have said this first couple days of class, the standard model, that chart right there, is kind of the crowning achievement, or at least one of the crowning achievements of physics. So this whole universe, this whole path we've been on for millennia of trying to figure out what the world is made of, like I've said, we're still only like 5% done, I think is a good guess. But we have that, which is a huge accomplishment. And what that chart represents is our understanding, and we think it might be done, that might be it, of what everything's made of. And so if I want to know what me, you, space, planets, sky, stars, even light are made of, it's those things. We think we found them all, which is crazy. It's crazy, I think, that nature was even kind enough to let us do that. I could imagine living in a universe where nature just kept everything behind a veil forever. And there's some things will probably remain behind the veil for a while, maybe forever. But at least we now feel pretty good that we know what the universe is made of, or at least what stuff is made of. And so this semester, we're going to boil down to those fundamental particles. We're going to talk about a few of those anyway. So those are the fundamental particles. I think I mentioned on the first day of class that one of the ways you can describe the history of physics is this pursuit to kind of drill down, and we keep finding that everything has substructure, so you can keep chopping an apple in half, and eventually you get to little bits, and those bits can get divided, and those bits can get divided, but eventually you get to something indivisible, and those are them. Those are our indivisible things. Atoms are a misnomer. They're not atom. They're not cuttable. You can cut an atom into bits, but eventually you do get to something atomic or fundamental, and that's them. So we've been trying to figure out what light is for a long time. It makes sense, if you think about the history of it, it makes sense to think, okay, light is, if I'm trying to observe it, if it's something I'm trying to study, I'm a scientist, I'm trying to figure out what this stuff is. I can't hold it, I can't contain it. It does seem to be everywhere. There's more of it at daytime, but there does seem to be a lot of it. But here are some things I can observe about light. It does bounce off things. So if I have a shiny surface, or even like a surface of a pond or a puddle, I can see that light, I can see the sun in a puddle. And so if I'm trying to study light, there's a clue. And so this light apparently coming from the sun, whatever the sun is, and whatever it's producing, not sure, but it's coming down, hitting the puddle, and coming back to my eye. And in fact, if it's shiny enough, I can recreate images. So that looks just like the sun, and oh, that looks like me. And so I can see that something is bouncing off of me, then bouncing off the puddle, and bouncing into my eye. And that right there gives us a picture of light as a thing, as a particle. And the early theories about light were that light was a particle. And that makes a lot of sense. It bounces off things. You can catch it. And if you catch it, things get warm. So these are things that we've observed. So it makes sense to think of it as this bit or particle. And that also goes along with, let's see, like 1800s. That goes along with the rest of our view of the world. The world is kind of made of bits. So you and I are made of bits called atoms. Atoms are made of protons, neutrons, electrons. Light itself maybe is a bit. And that was a pretty compelling theory for a long time. And then, let's see. Where's my first example? Well, I think here's our first example of that maybe not working out so well. Actually, let's go, we're going to get back to let me give you a little bit of background. So here's something we know, not about bits, but about waves. So up here I have my water tank. Let's see. I'm going to turn the side projector off for just a second. So up here I have my water tank, and you can see, let's see if I turn this guy on. You can see a projection of the water. So this thing has like a ½ inch of water in it, and you're seeing the light being projected through the ½ inch of water. And on the left, you can see a boundary with 2 openings in it. So I've got a wall. That's what you're seeing, the vertical dark thing. That's a wall with 2 openings in it. And just to the left of that long black tall stripe right there, that long black tall stripe you're seeing is a little gizmo that will move back and forth. So this is like a miniature wave pool. So if you've ever been to, I forget the names of some fun park or something, the big wave pool. So the wave pool, the way that works is there's this big thing just moving back and forth. You ever tried that in your bathtub or something? Like imagine sitting in your bathtub holding a lunch tray or something and doing this. You can make these nice planar waves. And so that's what this gizmo does. That black thing on the left makes these nice planar waves. Here's what you're going to see, which is interesting. When those planar waves get to those openings, they're going to pass through the openings. That's what waves do. There's no impediment there, and they're going to pass through. But waves do something interesting, and this is the reason for this little demo. Waves, when they get to an opening, spread out. Waves, you might expect that the wave gets those 2 openings, and you get 2 little like rectangular or square waves just kind of propagating from left to right on the screen. But that's not what happens. I don't get like a little mini wave just cruising along at, in real life it's 1 centimeter on the board up there. It's like a foot. So I don't get this like little square wave moving through. What happens is as soon as it emerges from the opening, it disperses, and it actually goes out in a little circle. And it actually is almost exactly like you would just drop, a pebble into a pond. You get these circular waves. So let's try that. Let's get my... That's pretty good. Okay, so that's what you're seeing right now is that black thing on the left is creating these planar waves, and I'm getting these planar waves going straight toward the boundary. But when they arrive at the boundary, they have these 2 openings, and I think hopefully you can see these semicircular patterns that emerge. So what happens when a wave hits an opening, it spreads out like that. And so that's what we're seeing here. We're seeing 2 semicircular waves emerge from the wall. Hopefully everyone sees that. Now here's the key. Here's the kind of important thing to see up here, is when you get two, so I could just have one opening and I would just have this nice little rainbow pattern going forward. But when I have two openings, I'm going to get a pattern of interference or overlapping. That's called an interference pattern. That's a very, very important concept in physics, an interference pattern. And so what you're looking at is an interference pattern. The reason you're seeing an interference pattern is because light, well, I shouldn't even say that, because waves are waves. Waves, if you've ever drawn a wave, they have high points and low points. Waves are additive. So if a high point and a low point meet, they can cancel. If a high point and a high point meet, they can constructively interfere or add. And if a low point and a low point meet, they can constructively interfere and subtract, I guess. But like I said, if a high point and a low point meet, it's called destructive interference, and they can cancel each other out. I think you could imagine that if I have a wave amplitude going up and down, and I add it to another one that's exactly opposite, they'll cancel out. We don't really get into sound in this class, but that's how noise-canceling headphones work. It's a really smart idea that instead of, if I want things to be quiet, one way to do it is just like wrap my head in bubble wrap until everything is muffled. A better, smarter idea is I just take little headphones that have microphones on the outside. They listen to the outside sound. They flip it upside down and play it into my head. And so actually, noise-canceling headphones aren't noise-canceling at all. They're noise-producing. They just produce a noise that is exactly upside down of the ambient noise, and you hear nothing as a result. It's a crazy idea, but it totally works. So all that to say, waves can cancel each other out. So what you're seeing up here is two sets of waves, and hopefully you can see a pattern of canceling. And the pattern of canceling goes out in these rays from the source. So if you look really closely, you should be able to see these rays kind of emanating from the halfway between those two spots. Little rays of interference. If I mess with the frequency, I might be able to make those rays more pronounced. So yeah, you should see these rays, these patterns where it's like dark, light, dark, light. Hopefully we can see that. So what that pattern you're seeing is being generated not from 2 point sources, and that's a really important point right there. It's not from 2 point sources. That pattern is being generated from one planar wave source and 2 openings. So with 2 openings and 1 planar wave source, I get an interference pattern. Okay. And so the last thing I'll say about that is imagine if you had on the far right, you had a detector. What that detector would detect is alternating spots of high amplitude, low amplitude, high amplitude, low amplitude, high amplitude, low amplitude. That is what we call the interference pattern. The interference pattern is what I would detect on the far right over here, what I would see. Okay. So far, that might sound, why do you care about what patterns show up on the far wall of a swimming pool if you've got a planar wave and a wall with 2 openings in it? That's a little obscure. Because something that happened right around 1800, right around the turn of the century, right around 1800, we discovered something, not about water waves. Oh, I was waiting for that to turn off. Not about water waves, but about light. And so let's look at another example. Go there. Let's actually go here. No, let's go here. Oh, there it is. Okay. Okay, what you're seeing right here, let's see if I can pull this all the way up. Okay. Okay, what you're seeing right now is a laser. And then if we have time today, we'll actually talk a little bit about what lasers are, because they're light, and that's what we're talking about starting today. But for now, all you need to know is that's a laser, and that's laser light. And we probably have played with laser pointers. A laser light is it's just a beam of light. And so here in 1800, here's what a scientist in 1800 is thinking that they're looking at right now. And this makes sense. This is not crazy to think this. That what I'm looking at is some source of red light. I'm not exactly sure what's going on in there. Some source of red light, and it's shooting little light particles, little beams, little light balls or something like that. And they're flying through the air, and they're hitting that screen, and they're bouncing off, and I can see them. So that's a pretty good, I think that's not a bad way to imagine what's happening right now. and I could, if I had a mirror right here, I could bounce them off that mirror and I could shoot them all over the room. So totally reasonable to think of light as these little particles, little balls, little projectiles or something like that. So here comes a guy named Young in the early 1800s, and he says, okay, that makes sense. What we're looking at right now is just boing, boing, little balls of light shooting off, bouncing off that boundary, off that screen and hitting me in the eye. Then what Young does is he takes that little source of light, these little balls, and he passes them through two openings. And when he passes them through two openings, like I have up here, let's do this one. That's what he sees. And that right there is crazy. If you, I want you, maybe after, on your way out of class, like, look at that. Make sure, you know, don't take my word for it. Look at that. What you're seeing up there is the result of just two openings. And as a scientist in the early 1800s thinking, okay, light is just little particles, imagine a wall with two openings in it, and you shoot particles. You're going to get some particles going through the right opening, and some particles going through the left opening, and what will show up on the screen is two stripes. The fact that more than two stripes show up is kind of mind-blowing, because I promise you there's only two openings in that little screen. And so what is happening, the way we can interpret, pretty safely interpret what's happening up there, is that light is a wave. And just like that property, just like what we saw up here with the water, light is doing the same thing. Light is going forward like a planar wave. It's just traveling as a wave. It's arriving at a boundary. That boundary has two openings in it. And those two openings aren't just letting light go in two little beams. Now, I think you can imagine, like, in your house sometimes, if the blinds are just a little bit open, you get stripes on the other side of the wall. That's what's going to happen at a large-scale perspective, because what we're doing right now is very, very small, down at near the wavelength of the light. So if you just have, if you open a window in your house, you don't get like 40 windows on the other side. You just get a beam of light. So again, it makes sense to think of light as just projectiles, because it often behaves like that. You have to get down to a very, very small, like nanometer-sized scale, till these weird properties of light start showing up that make us question whether light is actually a particle or a wave. And this is called the Young double-slit experiment, and it's our maybe not the first, but at least our most famous big aha that light it has to be, unless some other crazy thing is going on that I don't know about, light has to be a wave. And for about the next 200 years, we went through this whole, light's neither a particle nor a wave. It's got a wave-particle duality. And I think if you were to Google wave-particle duality right now, that's still a theory. I think physicists are just starting to accept the fact that it's kind of hard to swallow. We were just wrong for that long. It's just a wave, I think is probably a safe bet. That this whole duality thing is overly complicating things. It's a wave. Light's a wave. And I think that we could probably just settle there. Okay, but I do want us to see that, because that's crazy what's going on there. That the light is passing through two openings, and you might expect two dots, but you get this light is interfering with itself, which when you watch water do that, that's kind of neat, but not totally mind-blowing. I think that's crazy that light is interfering with itself. So what you're seeing is light canceling itself out in some spots and adding to itself in some spots. And what I might eventually get to later this semester, all of these guys will do that, which is crazy, because the guys on the left are actual physical matter. You can get physical matter to go through two things at the same time and interfere with itself. It's counterintuitive and hard to swallow, but yeah, that seems to be the nature of the universe. Seems to be the nature of all things, is that they will do that. Okay. So we come up with this idea that light is a wave. Here's the next question. A wave of what? And so here's Young double-slit experiment, early 1800s, saying, okay, light's a wave. And physicists will say, okay, I'm convinced by the interference pattern. Interference pattern is a pretty convincing argument that we've got a wave up here. A wave of what? Because any physicist worth their salt in the early 1800s knows that waves are in a medium. You have to have a wave of something. You don't just have waves of nothing. You need a medium. And so thus begins this great search for the medium. And so physicists start thinking, okay, what is the medium? What is waving, right? So something has to be waving. And if you think about it, the most abundant source of light back then and still today is the sun. And so when I go outside at the daytime, I know the sun is very far. And if I am looking at the sun, if I am seeing sunlight, there is a medium between me and the sun, because I'm seeing waves of light come from a very, very, very long far away to me. So there has to be a medium between me and the sun. So when I'm seeing light in the room, I might think, okay, that's the air is doing something. But I have to think a little bigger than that and go, wait, if light is a wave and there needs to be a medium, that medium must be all-pervasive, because I'm getting starlight. Forget our sun, that's really close on a cosmic scale. I can see things that are hundreds of thousands of light years away. How is that happening? What is this interstellar stuff? And so thus arises the idea that there's a luminiferous ether. There's something between us. There's something that just permeates all space. And it must glow, and that light is a wave in this ether. So this is one of the more famous one of the more famous successful physics experiments. One of the more famous failed physics experiment is also worth talking about. I don't know if this comes up in like a high school physics class or anything, but the Mickelson-Morley experiment. These guys, poor guys, Mickelson and Morley, the Mickelson-Morley experiment, they are famous for the greatest failed physics experiment ever. That's how they got their name, is they tried and tried and tried and tried and never got anywhere. And so you can imagine these guys, they're going, oh, we're going to be famous. We're totally getting a Nobel Prize for this. We're going to make this. They have this really great idea. And I don't know if you've everyone needs to fail in a lab sometimes. It's a tough thing to go through, to spend like a week set up and get everything right. You got your lasers and your mirrors and everything set up, and you've thought through every possible thing this way could screw up, and you turn it on, and it's just nothing. And you fail, and you get a 0 result. So you go back over your math, and you go back over it, and you try again, and you get nothing. Well, that's what Mickelson and Morley did for, I forget how long, decades, I think, that they were working on this. But thank you to Mickelson. I mean, it was tough. It was a tough road to go. I mean, you don't get I don't think you get a Nobel Prize for a no result. But thanks to them, we really ruled out what they were searching for, which I guess is a success. But and so what they were searching for is the medium. And so here was their idea, and it was let's see. I don't think I do have a picture. Okay. Let's see. It's that. Okay. Here's what they came up with, and that's called an interferometer. That's called an interferometer, and that is a picture. It's a schematic of the Mickelson-Morley interferometer. Here's why I think another reason this is interesting. You may recognize that setup. I've described it once already this year. That's how LIGO, the the first two letters, Laser Interferometer Gravity Wave Observatory, that's how LIGO found gravity waves. LIGO, I've described before, is this long hallway, 2.5 miles long, and at right angles, another 2.5 mile long hallway, and they bounce lasers back and forth. That's an interferometer, and that's a picture of an interferometer, where I've got a laser source on the left. I send my laser through a half-silvered mirror, this clever device that they came up with a long time ago. You take a piece of glass, it's pretty transparent, you silver it, it's a mirror, you only silver it a little, and half the light will go through and half the light will bounce off. And now there's your beam splitter. So you take a beam splitter, put it in the path of your laser, and you can split the beam into 2 orthogonal paths. So you can see that the coherent light source on the left goes straight through the mirror and hits the mirror on the right. That's the orange beam. 50% of the laser goes straight through and hits the beam on the mirror on the right. The other 50% actually reflects and goes north, hits the mirror on top. Both come back to the mirror and then go to the detector. If both legs of that mirror are exactly the same length, the laser actually cancels itself out, and I get nothing in my detector. And that's how LIGO works. LIGO has these 2.5 mile long hallways bouncing lasers all day long, and there's supposed to be nothing there. Now in LIGO, what happened is a gravity wave passed through the interferometer, shortened the length of one of those legs, and all of a sudden a laser showed up in the detector. So the laser was not perfectly canceling itself out anymore. It was a little bit offset due to the change in length. And hey, we just discovered gravity waves. Here's what Mickelson-Morley proposed. Mickelson-Morley proposed that, okay, space is filled with this stuff that light is a wave in, so this ether. So there has to be this stuff. Well, the Earth is not stationary. The Earth is orbiting the sun. So the Earth must be plowing through this stuff all day long. So here's how we're going to detect the presence of the stuff. Is if the Earth is plowing through this stuff all day long, we're going to take an interferometer. Theirs was not 4 kilometers on either side. Theirs was like, I think about like 10 feet across or something. We're going to set up this nice laser experiment, and we're going to, you could do the math. You could go outside and figure it out, that they're going to orient their device such that one of the legs is traveling through the ether in the direction of the orbit of the Earth. So as they're cruising, as they're doing their experiment, they know that one leg is going to be plowing through the ether. The other leg will be at right angles to the ether and just moving that way. And if the ether is stationary and the Earth's plowing through it, that will actually shorten the wavelength. It's a wave, right? And if it'll kind of crunch the waves. It'll kind of crunch the waves in the direction of travel and not in the sideways direction. Genius idea. And you can kind of do a test and tweak one leg length, and you'll see that that actually works. But they just never got a result. That both lasers always came back to the exact same place. There was never any difference. And they would turn it 90 degrees, and they'd wait till summer, and they'd wait till fall, and go over and try it in Belgium, and it just never had a result. I do have one. I guess I could show a quick example of what we're talking about when I mean interference with a laser. So here's a crazy bright green laser, and this is not a half silvered mirror, but it's close. This is a pretty silvered mirror, or a barely silvered mirror, I guess I should say. If you look, this laser is going in a straight line, passes straight through this angled, you can't see that, this little angled, it's actually a microscope slide back from biology days. It's going through a microscope slide, and it's hitting that wall over there. So I think everyone can see a big, bright green spot of light. But it's also, some of the laser light, because it's at a 45-degree angle, is actually bouncing straight through this lens right here and is hitting my screen. So hopefully everyone can see that green spot right there. Notice the green spot over there is just a bright spot of green light. There's no weird pattern. Your eyes kind of play a trick on you and make you think it's twinkling or something, but it's just a green spot over there. But hopefully you can see on this screen there's a pattern, maybe from where you're sitting that's visible. There's a pattern of interference. And what that is showing is because this microscope slide, back from your microscope slide, biology days or whatever, has a non-zero thickness. So some of the lasers actually bouncing off one surface of the slide. Some of the lasers actually making it through the thickness to the opposite side and bouncing off. And so you're actually getting 2 beams of light coming out of this reflection and hitting that screen. That is what happens in an interferometer. That's what Mickelson and Morley were expecting to see. That's what LIGO saw. That is an interference pattern, not from 2 slits, but similar. Not from 2 slits, but from actually 2 sources. So anytime you have something with a little bit of thickness, you can get that result. And so some of the laser light is bouncing off the front, some of it's bouncing off the back of the microscope slide, and we're getting an interference pattern. Okay. Cool. I'll turn that off, otherwise someone's going to walk into it. And that is not the kind of laser you want to walk into. I'm looking for the wattage, but trust me. Okay. So Mickelson and Morley go through this whole experiment, and we find there is no luminous ether. What is it? So physicists continue to work on it for a while. Guess who's one of the guys who helps figure it out? Einstein. He's good at stuff like that. So Einstein, another guy named Maxwell, we eventually figured out that here's what light is a wave of. First of all, it's a wave in space itself. You don't need a medium. Space is the medium. Or I should say, maybe a little more accurately, space, and I've said this enough in this class, so hopefully we're starting to realize this. Space is not empty. There is no such thing as empty space. So take all the planets, all the gas, all the stars, all the light out of the universe. What you're left with is this medium that we call space or space-time, and that medium has some really relevant non-zero properties, and one of one of those properties is its ability to carry electric fields. Electric field, that's a phrase I've not uttered this semester, electric field. We'll actually talk more about what I mean by that, but electric field is, it's a thing that will push or pull on electric charges like protons and electrons. Maybe that's all we need to know right now. So an electric field, yeah, maybe I'll describe it that way. I should slow down a tiny bit just to say that this idea of fields is maybe one of the, I don't know if I've said this about other things in this class, so I'm probably contradicting myself. Maybe one of the more important concepts in physics is the idea of fields. And so if I can think of space as a field, as an area of influence. And so all of space is a field. It's an area that can be manipulated, that can carry pushes and pulls, I guess, or forces. And so an electric field is space pushing or pulling on a positive or negative charge, on a charged particle. Okay. So that's an electric field. A magnetic field is the same thing, but for magnets. So it's a field of magnetism. It can push or pull on other magnets. So if you've ever, like, if you ever had static cling or something like that, or that's electric fields. If you've ever rubbed a balloon on your head and stuck it to the wall, that's electric fields. So I think we're familiar with electric fields. It's just an area of influence. And that happens over a distance, which I guess is important. So yeah, we'll talk more about that later. So it happens over a distance. If you ever taken two magnets and put them up into each other, they know each other are there, right? Like you can feel those magnets attracting or repelling before they touch, which is crazy. I think everyone should take a second and next time you're holding a magnet and it is attracted to something metal or attracted or repelled from another magnet, take a second and realize there's something doing communicating. That's kind of crazy that those two magnets know each other exists. Well, it's magnetic fields. And we'll talk more about some of the details of magnetic fields later, but Maxwell comes along and Einstein, I think, kind of proves it that here's what light is. It's a wave in space. You don't need a medium. And it's a wave of electric and magnetic fields. And that picture right there is actually a pretty good picture. That's not just some artist rendition. That's actually a pretty good picture because when I say it's a wave of electromagnetic fields, it's both at the same time. That's what you're seeing in that picture. It's an electric field oscillating up and down, positive, negative, and a magnetic field at right angles. And so that's actually a pretty good picture. So hopefully that representation, you can see that that's what that's trying to represent. You actually have a up and down wave of electric field and an orthogonal or right angle wave of magnetic field. Now, quickly I should clarify, the light is not doing this. Light does not, you can't like duck light as it waves over you or something like that. Light is going in a straight line, but that thing that's going in a straight line is two waves of electric and magnetic field. And so light is traveling in a straight line, so it doesn't do that. But while it travels, what is traveling? What is traveling? What is traveling is a wave of electric field and a wave of magnetic field. Yes? Great question. She asked, is it going up and down or is it left and right? It's totally random, but they're always at right angles to each other. And so if I turn on this light bulb right now, if I turn on that light bulb right now, the light that was hitting you was just totally random. There was probably some doing this, some doing this, some doing that, some doing that. But at right angles to that direction was a magnetic field. So I shouldn't say up and down. I should just say it's a wave going some direction and a magnetic field going at right angles to that. That's hard to do. I'm trying to get my hands to do that. Okay. Good question. All right. In the room? Yeah, question. Does it go through? Yeah. That's a great question. The question was, does it go? Yeah. Here's the thing, and I think this is where I want to get today. We've got 9 minutes left. That's kind of where I want to get today, is that, okay, light is this electromagnetic wave, a wave of electricity magnetism, otherwise called electromagnetic wave. And it has very differing properties based on only one thing, based on its two things, based on its wavelength or frequency. And let's pull, to do an iClicker. Yeah, okay, we'll do an iClicker in a second here. Let's prepare for iClicker. Okay. Yeah, we'll get to this. So, here's my one equation. This one equation will get us probably a week or two in this one equation. Here's my one relationship. It's not an equation. Here's my one relationship. Here's what that relationship is saying. All light goes the speed of light, right? That's kind of goes without saying. Light goes the speed of light. That's c over on the left. That's the same c that shows up in E equals mc squared. That's c. That's speed of light. I think when you get out of this class, I'm only going to hope that you have a couple numbers in your head. 9.8 is a good one to have. Here's one that's great for parties. Everyone wants, you want to be the person in the party that actually knows the speed of light. Everyone knows it's fast. You should be the one that knows it's 186,000 miles a second. That's how fast. 186,000 miles a second, or 300 million meters per second. That's how fast light goes. It's 300 million meters per second, 186,000 miles a second. Now, that's a constant. It doesn't change. You can't. So that c on the left is always the same number. So here's why I want you to even know that equation. The two other symbols, that's lambda on the left, lowercase lambda, and frequency. Lambda for wavelength and f for frequency. Lambda means wavelength. It's literally the length of the wave. So how far it takes to go up and down one time. How far that takes. And frequency is how often, measured in per seconds or hertz. So if you ever heard of a hertz, hertz is how fast or how cycles per second. It means per second. So when you tune your radio to 106.1, that's 106.1 megahertz. That's a million times per second. So that the wave in your antenna, when you're listening to 106.1, the wave in your antenna is going up and down 106.1 million times a second. It's very fast. So we can cram a lot of data in that wave that small. Question. Oh yeah, it goes through stuff. Yeah. So it's crazy. So this thing called light, this thing called light. Here's some other things you need to know about light. It's massless. It's chargeless. It's sizeless, and it always goes the same speed. So that sounds like a pretty benign, boring particle. It's massless. It's chargeless. It always goes the same speed, and it's sizeless. So it's pretty much nothing, right? It's got no size, it's got no charge, it's got no mass, and it's just always going the exact same speed. So that doesn't seem to be very exciting. But all you have to do is change the one of those. Let's say lambda, the wavelength. Obviously, if you change lambda up, frequency has to go down because c always has to be the same. Or if you make lambda smaller, frequency has to go up. All you have to do is change one of those, and its interactions with matter changes drastically. And so I can take a beam of light, and it'll go straight through me. And I change the frequency, and it bounces. And I go change the frequency, and it goes halfway through me. I change the frequency, it sticks in me, and I change the frequency a little more, and it bounces right off of me. And so we'll get more into that, but short answer to your question, all of the above. It does all kinds of things just based on the wavelength and frequency. Okay, so speaking of wavelength and frequency, here's our iClicker for the day. iClicker is microwave ovens use 2.4 gigahertz frequency, radiation. So that means that the wave in your microwave is going up and down 2.4 billion times a second. That's insane. A second is like not a ton of time. And a microwave goes up and down 2.4 billion times. I want to know, given that little bit of knowledge, oh, I have to hit start, don't I? Oh no. iClicker not responding. Oh no. Let's see. There it goes. So given that bit of knowledge, there we go. If your microwave cooks food and boils water and heats up your tea and your coffee, it's going 2.4 billion hertz. Take a guess, if that's how you cook coffee, what does it take to send us a text message or a snap or something like that? Let's take 40 more seconds, 30 more seconds. microwaves operate at 2.4 billion hertz. Cell phones, A is around 100, B is around 1,000, C is around 1,000,000, D is around 2.4 billion. All right, take 10 more seconds. Okay. So tempted to, yeah, no, we should go over this. The answer should concern you. The thing that you can just totally destroy a piece of chicken with is the exact same stuff your cell phone uses. It's D, it's 2.4 gigahertz. And like I said, if you go back to the equation I had on the board a second ago, the only thing that defines the property of light is its frequency, F. So there is very benign light that doesn't hardly do anything. Very low frequency light. Give me 2 more minutes before we back up. 144. It's only 144. So there's very nice benign light. But 2.4 gigahertz is a little more energetic, and you can do some crazy stuff. If you've ever over boiled some water or totally forgotten to take it out and mess something up, that's the exact same stuff your cell phone uses to communicate. So maybe we'll end with this public service announcement. Guys, take it out of your pocket. Everyone, don't hold it next to your thinking organ all day long. And so that same stuff that cooks food is also being generated all day long. And you don't have to be on a phone call. Your phone is talking to cell phone towers all day. Now we'll talk next class. I'm not trying to say your phone's going to kill you. We'll talk next class about how that's not that bad, but all right, we'll see you Wednesday.